So our next presenter is John Percy, and we'll go to fun facts for a moment while we switch over to an online presenter.
I'm a supposedly retired professor of astronomy and astrophysics at the University of Toronto. I'm an associate member of the Dunlap Observatory, Dunlap Institute. My first 40 years were at the University of Toronto, Mississauga, where I was a founding faculty member. If you don't happen to know, I'm a former national president of the RESC, former honorary president, fellow of the RESC. So the RESC is in my bones. I edited the Observer's Handbook for 10 years. I have a column in the journal, which I hope everybody reads every 2 months. Okay, well, thank you very much. I'd like to start by thanking the tech team for sorting out the technology here, and also for having me back after the technical problems that we had last time. It turns out that what I want to tell you about follows up quite nicely from where Andy left off with the discussion of red giant stars and the important work that skilled amateurs can do in making observations of these stars. So this is what a red giant looks like. This is a high resolution image from the European Space Agency. And red giants are dominated on their surface by huge convection cells, which you can get a sense of in this picture here. In the Hertzsprung-Russell diagram, which many of you are probably familiar with, that plots luminosity vertically, temperature horizontally, red giants start out like stars like the sun. And as they exhaust their hydrogen fuel, they swell up, become red giants. Then they ignite their helium fuel and they start to exhaust that. They swell up some more, becoming even larger red giants. But at this point, they have a strong stellar wind and they lose about half of their mass. It's cast off in the form of a planetary nebula, and the core of the star shrinks down and becomes a white dwarf star. So this is basically their life history very quickly. And this is an image which shows something of the mass loss that goes on when a red giant expands to its full size and its full luminosity. It can lose about half of its total mass in mass loss. And we believe that the mass loss is driven by the fact that the star is also pulsating. And interspersed among this mass loss are things called helium flashes, which are nuclear instabilities in the interior of the star. And so you can see that the mass loss as it drifts out here is not completely uniform. The other thing about red giants, and this is what's always interested me, is the fact that they pulsate. They're unstable to low order radial pulsation, that is in and out pulsation. And the pulsation period and amplitude tend to increase as the luminosity increases. So there's a period luminosity relation. So a low luminosity red giant, shown on the left here, might pulsate with a period of, in this case, 31 days, about 1 month. The amplitude is measured in hundredths of a magnitude. A more luminous red giant, in this case with a period of about 100 days, has an amplitude of measured in tenths of a magnitude. And the Mira stars, which were alluded to earlier, these are the highest luminosity red giants, has a period of 413 days. And you can see that the amplitude is measured in magnitudes. It amounts to 3 or 4 magnitudes in total. So, in addition to that, it's been known for almost a century that many red giant stars also have a second period, and it's 5 to 10 times the pulsation period. This particular table here is taken from a monumental paper by Cecilia Payne-Gaposchkin, who is arguably the greatest woman astronomer of all time. And you'll notice these are the pulsation periods, and in this third column are the long secondary periods. And Nancy Houck in 1963 provided a list of over 100 of these stars, which had been accumulated mostly by photographic photometry at the Harvard College Observatory, which is what HCO stands for here. Incidentally, the people that did most of the work, the research assistants at the Harvard College Observatory, were virtually all women. And some of them became very famous, and their names are in textbooks now because of the things that they discovered. They were unfortunately paid less than male research technicians would be paid. That was the way it was at the time, but I suppose the director's budget went a little bit further. Now, just as an aside, I looked at Houck's list here, and there were 37 stars that had good follow-up observations for several decades. And I redetermined their periods of pulsation and also their long secondary periods. And in 33 out of 37 cases, the periods that I found were the same as the ones that were listed in Houck. So with photographic photometry, they were 90% accurate in determining the periods of these stars. Another interesting development is that all of this Harvard College Observatory photometric data is being digitized in a project called DASH, Digital Access to a Sky Century of Data at Harvard. This project is coming along rather slowly, but it'll be very interesting to have all that data available. Now, what happened was that Harvard basically phased out its photographic photometry program in the mid 20th century, but very fortunately, skilled amateur astronomers through the American Association of Variable Star Observers, which has already been mentioned, picked up the baton there and ran with it. In this light curve here, magnitude brightening upwards, time along the bottom. This is almost a century of data here on a star called Y Lynxus here. And this star has a pulsation period of 134.7 days. And what we've done here is to basically bin or average the data in 134-day bins. And now you can see in red here the long secondary period. You can see how consistent it is here. Its value is 1,259 days. This particular work was done by a brilliant undergraduate student, Emily Diebert, and followed up by another student, Henry Leung, who's just completing his PhD in the astronomy department. He's one of my colleagues. And so this kind of data is available for dozens of red giant stars. And it was mentioned earlier how useful it would be for some of you to go out and observe red giant stars. And this is the kind of science that can be done with it. Now, about 1980, a couple of developments took place. One is that robotic telescopes started to be developed. And some of the early work was done by amateur astronomers such as Russ Genet. This particular light curve here, this is about 10 years of data on a red giant star here. On the right is one season of data, so you can see the pulsation period here. But you can see over here the long secondary period that's in this star, which is about 10 times the pulsation period. This is from some work that was done in collaboration with Greg Henry at Tennessee State University. He had access to a robotic telescope. Joe Wilson was an undergraduate who actually did the analysis here. So we have data on about 24 of these red giants. The other thing that happened at the same time was that amateur astronomers got into photoelectric photometry in a big way because photometers could be obtained now off the shelf from people like Optech and so forth. So this is some work done on a very famous red giant EU Delphini here. And again, it's a light curve here. We have something of the order of about 1,000 days of data here. And in red, you can see the long secondary period, and the scatter up and down is the pulsation period, which is about 60 days. So the amateurs were really picking up the baton here and continuing the observations of these stars. And their observations are particularly important for long-term variations in stars, such as these long secondary periods. But in the 1990s, there was a huge development among professional astronomers of automated surveys of the sky. And three of them in particular, there was the All Sky Automated Survey. Macho was massive compact halo objects, and it and Ogle, the optical gravitational lens experiment. They were particularly to look for gravitational microlensing of stars by compact objects like black holes or neutron stars or white dwarfs in the halo of our galaxy. And so they were accumulating automatically data on thousands and thousands of stars. And this is some work published by Peter Wood in Australia. Again, this is a period luminosity relation. That's luminosity increasing upwards. These are stars in the Large Magellanic Cloud, and along here is the logarithm of the period. Now, in this graph, you will notice a number of sequences, sequence A, sequence B, and sequence C. And these are pulsation period luminosity relations for the fundamental mode, the first overtone, and the second overtone. But on the right, you see this other sequence, sequence D, and this is a sequence of long secondary periods in these stars. And Peter Wood estimates that about a third of red giant stars in his survey show long secondary periods. So it's a very common phenomenon. And so this aroused a great deal of interest and activity in trying to explain this phenomenon that occurred in about a third of all red giant stars. Peter Wood maintained that it was the only unexplained type of large amplitude stellar variability known at this time. But there were a number of possible explanations, of which non-radial pulsation was one, possibly turnover of convection cells, and quite possibly binarity, that it was some kind of eclipse phenomenon or something else. A lot of people worked very hard on it. One interesting thing, and this is harking back to the AVSO again, low mass yellow supergiant, stars that are in transit between the red giant region and the main sequence and white dwarfs, do the same thing. And here we have something of the order of 10,000 days of data here. Every point is an observation. This is the long secondary period in this star. It's 2,500 days. In this case, this is known to be due to binarity, except that the eclipses change their character with time. So it isn't some constant object that's doing the eclipsing. It must be something that varies, such as a cloud of dust. But there was a kind of a red herring, and that is that when you made radial velocity variations, which is usually the way that you would detect binary motion, that when you took the velocity variations of the red giant, they all had a very unusual shape. They weren't sinusoidal. They had exactly this same shape, no matter which star that you looked at. And that meant that all these things not only had to have the same shape of the light curve, but they all had to be oriented in the same direction, which makes absolutely no sense at all. So finally, a reasonable solution came along from Igor Sosinski and his colleagues in Poland, who maintained with strong evidence that the long secondary period light changes are due to the presence of a dusty cloud orbiting the red giant together with a companion and obscuring the red giant once per orbit. So it was an eclipse. But the companion began as a planet and then accumulated mass from the wind of the star to become a brown dwarf or a low mass star, which would produce the radial velocity variations that we see. And so here's an illustration of this. It's by Matilda Sosinska, who I assume, since she's of age 12 years old, that she's a young relative of Igor. And so this is what they proposed is going on. We've got our red giant star here. We've got a dust enshrouded companion here that's going around every LSP. So that's the long secondary period. The strongest piece of evidence is when you observe this phenomenon in both the visual and the infrared. In the visual, you only get one cycle, the one long period, long secondary period, which in this star is 417 days. But when you look in the infrared, there's a secondary eclipse halfway between the eclipses due to the primary eclipse. And if we go back to look here, then that's because the dust enshrouded companion here is cool. It has a temperature of maybe 1,000 degrees. And so it's an infrared source. And when it goes behind the red giant, this infrared source gets eclipsed. And so we get a second eclipse in the light curve here, as well as the ones due to the eclipse of the red giant. Now, I've identified 4 problems with this theory here. The first is it seems rather puzzling to me that if a third or as many as a half, because some of these systems are going to be seen face on, in which case you won't see the eclipses, but the star will still have the same configuration. Well, these things must be among the bright nearby red giants that astronomers have been studying for 100 years. So it's rather puzzling to wonder why this phenomenon hasn't been discovered earlier. And it raises the second question, will the sun have a 50-50 chance of being an LSP star in the future? Something that should be looked into. Now, the second problem, which a student and I have been working on this year, is that it turns out that there are many stars in which the long secondary period is dominant over the small amplitude pulsation period here. This is data from the All Skies automated survey for supernovae, which we call Assassin. And in this particular star here, the pulsation period is 65 days, relatively short. The amplitude, as you can see, is only 1/10 or 2 of a magnitude, but the long secondary period is much greater than that. Now, I mentioned earlier that short pulsation periods and small amplitudes were what's found in low luminosity red giants, ones that haven't yet reached the stage of having extensive mass loss, which you would presumably need in order to get the planet, the companion, to accrete and become dust enshrouded. So this doesn't make too much sense, and it's something that we're continuing to pursue. Another problem is that these long secondary periods are quite common in red giants in globular clusters. Now, you may know that globular clusters are ancient clusters in our galaxy that have very low abundances of the heavy elements, the ones higher than, the heavier than hydrogen and helium. Well, those are things that you would normally need to make planets and to make dust and so forth. So it's rather puzzling then that there's enough planetary precursors and dust present in these low metallicity systems to produce lots and lots of red giants in globular clusters that have the long secondary period phenomenon. This was something that was originally done by Tom Lebzelter and Peter Wood, and a couple of my students have been continuing this work using the Assassin data. The fourth thing is that you'll notice that the sequences, and here I'm using data from Sosinski et al. For the Large Magellanic Cloud and the Small Magellanic Cloud. And again, you see the sequences due to pulsation, the ABC sequences, and the D sequence, which is due to the long secondary period. Well, notice how tight this relationship here is. It's just as tight as the pulsation ones. Now, the pulsation periods have a period luminosity relation because both the period and the luminosity depend very heavily on the radius of the star. But the long secondary period is the orbital period of the companion around the red giant. So the question is, why should the orbital rate, the radius of the companion's orbit, be correlated with the luminosity? Now, it turns out, in fact, it's a bit of a selection effect because if you read Szynski's paper, he only chose for the LSP stars the ones that lie on this sequence here. So he actually deliberately left the other ones off. But we can go back to Peter Wood's diagram, and again, you see that there's a narrow sequence here. So you can explain this by assuming that the orbit of the companion around the red giant is always about twice the radius of the red giant itself, which makes sense. I mean, it can't be much smaller than that, or the companion would be in the atmosphere of the red giant. And if it were too much more than that, then maybe it would be hard for the companion to accrete material, or the chances of seeing it in an eclipsing situation edge on would be much less. So maybe there is a solution to that. So I just want to leave you with this question that maybe you're asking anyway. Why does all this matter? Is this just some esoteric thing that professional astronomers do? Well, I mean, first of all, red giants are common. Look through your observer's handbook, Bright Stars, and you'll find that there's dozens and dozens of red giants. And someday the sun, in 5 billion years, will become a red giant as well. So this is apparently a common part of stellar evolution. The second thing is that apparently, if Szynski's theory is correct, then it requires the formation of planets, it requires the formation and accretion of dust. So maybe LSPs can provide useful information about these particular processes. And for me, it's interesting to think that maybe this century-old mystery, which both amateur and professional astronomers have contributed to, is finally solved. Well, not quite. So the work goes on. So thank you very much. I guess it's question time.
Thank you very much, John, for a very insightful presentation. Let's see, any questions in the room?
Hi, how large will these dust-enshrouded objects orbiting the giants be?
Well, I guess if you believe that artist's conception, which must have passed Igor Szynski's review, they are comparable in size to the red giant. But some of them may be smaller if the red giant is particularly large. This is something that we can presumably figure out from the depth of the eclipses. And the depths of the eclipses tend to be between 1/10 and half of a magnitude, which is not that much. So that suggests that the size of the dust enshrouded companions is somewhat smaller than the size of the red giant itself. That would be my guess.
Okay. Thank you, John. Any more questions in the room? Yes, we have one more here in the room.
So it sounds like your conclusion here is that these dusty companions are not likely to be the cause of this periodicity. Am I understanding that correctly, or do you think it is the cause?
Well, no, I really hope that Szynski's mechanism turns out to be correct. The evidence for it is really quite strong. It's just that there's these 3 or 4 loose ends that still need to be dealt with. And the other thing, I wrote a column about this in the RESC journal a year or 2 ago about the kinds of eclipsing stars in which the eclipser was actually a dusty object. You can actually go back and look that up. One of the kinds was the one I showed you of the yellow supergiant that had the 2,500 day eclipse period. And I, in fact, devoted a paragraph or two to the long secondary period stars. So I think this kind of phenomenon is probably more common than we might have thought. And so I think I'll still bet on Szyszynski's theory.
In spite of the likely lack of dust in globular clusters, and the fact that it just seems unlikely that these objects would persist long
Mhm.
enough to affect so many red giant stars. But do you
Well,
think there's enough strength in the theory that it's likely?
yeah, because if you believe Woods and Szyszynski, well, particularly Woods' survey using uh, using Ogle and so forth, at any one time, it looks like at least a third of red giants have these long secondary periods. On the other hand, I don't think the other theories work any better. A lot of attention was given to non-radial pulsations, that is, ones more complicated than just an in and out motion, and they didn't seem to work either. So right now, the evidence seems to favor the Szyszynski et al. Uh, theory. So we just need to clear up these loose ends, and that's what I'm doing right now, and other
Thank
people
you.
are
Thank you
too.
so much.
Okay, thank you, John. Any more questions in the room? No. All right. How about online, Emma?
Yes, you did get a couple of questions online. The first one comes in from Zappa and Zappa and wants to know, will you get swamped with data when LSST starts observing?
I'm sure that we'll get swamped with data when LSST gets started, but just because you have huge amounts of data doesn't necessarily mean that you can solve all of the problems. I mean, we had lots and lots of data in 1999 from Wood's work and others and so forth, and it still took us 20 years of thought and of looking at individual stars, like measuring radial velocities for a few. So often what happens is you get a huge survey, and actually by studying specific stars, you can get good information. And Andy earlier mentioned the idea of legacy stars in the AVSO. That is choosing a few stars that you observe intensively with the idea of understanding them as well as possible. So yeah, I think there'll still be a place for other kinds of observations.
Well, that's great. We got another question came in from Ron McNaughton who wants to know, is there a pattern to the multiple of the long and short periods?
Yes, the ratio of the long secondary period to the pulsation period tends to be either 5 or 10. And it tends to be 5 if the pulsation is in the fundamental mode, which is a longer mode. The first overtone, which is half of that, if that's the pulsation mode, then the LSP over the pulsation period is 10. So again, and this is going back to the business of the size of the companion's orbit compared to the red giant, uh, there is a kind of cookie cutter pattern to these things here. And always the red giant is the companion's orbit is about twice the size of the red giant, which produces this very nice relationship, which I showed you on the period luminosity relation, and gives you this ratio of either 10 or 5. And a very few have a ratio of about 14, which would be stars that are pulsating in the second overtone, which is an even shorter one than the first overtone.
Thank you. That's very interesting. Um, Ralph would like to know, would the dust enshrouded companions be pre-giant phase stars or already evolved compact objects?
They would be either brown dwarf stars or very faint main sequence stars with dust around them. And a very faint main sequence star is going to take tens of billions of years to evolve into a red giant. A brown dwarf will not evolve. It's too small, and the core is too cool for nuclear burning to take place. So they're basically small, compact objects surrounded by a cloud of dust that's been accreted from the red giant star.
Oh, that's very cool. Thank you very much. That's all
Yes,
for
it is
Physics on
very
the Go.
cool. That's what red giants are. Very cool. Thank you.
Questions, I guess, online or in the room? John, thank you so much for the presentation. I wanted to say something that right at the beginning of your talk, we didn't have audio here in the meeting room. So if you introduced yourself, we missed that. Now, I gather you're not a type of person who observes variable stars in the backyard with a 4-inch telescope, are you?
No, but I try and make good use of observations that are made by those people who do that.
But
So,
tell us where you are, what you do, and so on.
oh, okay. I'm a supposedly retired professor of astronomy and astrophysics at the University of Toronto. I'm an associate member of the Dunlap Observatory, Dunlap Institute. My first 40 years were at the University of Toronto, Mississauga, where I was a founding faculty member. If you don't happen to know, I'm a former national president of the RESC, former honorary president, fellow of the RESC. So the RESC is in my bones. I edited the Observer's Handbook for 10 years. I have a column in the journal, which I hope everybody reads every 2 months.